All right, so here's today's practice for stoichiometry. It's another stoichiometry problem. Except instead of just finding the excess reactant, you actually have to give me the pH at the end. Right, so start by writing out the reaction, make sure it's 1:1. All right, what are our products going to be? Okay. Lithium nitrate.
And hydroxide. Oh, it's like I used to call hydro.
What do you get when you add a hydroxide plus an acid? Bingo. So when hydroxide's acting as the base, it's only going to accept one H plus for starters. If water is acting as the base, that's when we get hydronium as the product. So first off, what's the pH of the nitric acid before the reaction happens? Before we add the lithium hydroxide, what's the pH? How do we know that? What is our formula for pH? Negative log of H3O plus. So here's a key aspect here. You guys want to pay attention to this part. The acids that we're dealing with right now are what are called strong acids. A strong acid in chemistry terms means that when you put it in water, it reacts with the water at 100% of the time. So if you put nitric acid in water, you get HNO3 plus H2O reacting to make nitrate. And when water is the base, we add an H plus to it. What do we get?
Hydroxide.
The other one. Hydronium. All right, so this happens 100% of the time with these strong acids. There's 7 strong acids that are really common. Don't worry about, well, we'll go through the list, but basically, if it's a strong acid, this process happens until you run out of the acid. Because if you're taking your acid and dissolving it in water, what do you have more of, water or the acid? Water. Here's a good trivia question. What's the concentration of water in water? If you have pure water, what's the molarity?
100.
What?
Close.
99.
55 moles of water per liter of water. If you look at the mass of water, figure out how many moles of water are in 1 liter of water, it's 55 moles of water are in 1 liter of water. Or we have 0.1 moles of nitric acid. So what's going to run out first? The nitric acid. All of this to say, if you have a strong acid in solution with water, like this, your concentration of hydronium is the same as your concentration of acid. Because every single acid molecule you have within sig figs is just going to react with the water molecule that it bumps into and turn into nitrate and H3O plus. That's the definition of a strong acid. Strong in chemistry terms means it separates 100% of the time. Right, we saw that with strong electrolytes when we started talking about solutions last, so that was probably the week before Thanksgiving. Right, so strong means this concentration is the same as this concentration. So does that make it easier to find your pH for the solution here? What's your concentration of hydronium in the solution? 0.10 moles. Right, this, if it's a strong acid in water, and all the ones we're going to deal with so far are strong acids, whatever your concentration of nitric acid is, that's the same as your concentration of hydronium. So if you want to know the pH here, it's negative log of 0.1. Anybody do that one in their head yet?
Oh, wait, no.
Log of 0.1 is -1. So -1 means pH is 1. All right, so that's going to be key for these strong acids. If you want to know your pH of a strong acid solution, just find your concentration of the acid. And your concentration of the acid is the same as your concentration of H3O+. Right? That won't change until we get into equilibrium in weak acids. Weak acids, you can't always assume this process is happening 100% of the way to completion. In which case you have to do more complicated math to figure out your pH of weak acid solutions. But for strong acid solutions, all you have to do is have your concentration of the acid is your concentration of hydronium. And just so you have a list here, I'm going to write out the list of strong acids for you. For now, we can assume that pretty much all of the acids we're going to be dealing with in these neutralization reactions, we're going to stick to, for the most part, stick to the strong acids. And it's nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Let's see, what am I missing? Perchloric acid. Is there only 6? Nitric. What am I? No, there's. What am I missing? Rena or Tom's. I feel like I was taught 6 and then I was told that there were 7 and I learned the 7th one and
It's HClO3.
HClO3.
Yeah.
Okay,
Yeah.
I got that one. Perchloric and chloric.
Yes.
Okay. This is not exhaustive. There are other strong acids. These are just the most common ones. Thank you for the assist. All right, so as long as your acid is one of these, your concentration of hydronium is your concentration of the acid. There we go. So our initial pH is 1, and then we add some solid lithium hydroxide to it, and we want to know that the new pH. So what if we have a chemical reaction? It's an excess reagent problem, right? We've done a bunch of these. They're not our favorite, but we're getting better at them collectively. So what's the next thing we do? Convert everything to moles. 0.125 liters times 0.1 moles per liter. That's going to give us 0.0125 moles. Right, 125.0 milliliters. Every 1,000 milliliters is 1 liter. 1 liter, 0.100 moles. Right, so we're gonna divide by 1,000 and then multiply by 0.1. Gives us a net result of 0.0125. And then how do we get to moles from lithium hydroxide? Molar mass. So 0.325 grams. Lithium is about 7 and then a 17, so about 24. Maybe 23.9 something. $6.9. It's actually going to be really close to 24 even, isn't it? No, 9.5. I can do math in my head. I promise. Right? Does that look like everybody's molar mass? Yeah. Cool. So we're gonna get something pretty close to 0.0125, right? 0.01.
0.0135. 6.9.
So we'll go 136 for sig figs. We'll have 3 sig figs here, right? So with this being everything being nice and 1-to-1 here, pretty easy to see what's going to run out first, right? We're balanced with it being 1-to-1, so that means we can just compare moles to moles, right?
Yeah.
Whatever we have less moles of is what's going to run out of first. So what's our excess going to be in this case? And then by how much? Yeah. We want to show the work here. We can say moles of nitric acid. For every 1 mole of nitric acid. If it's not a 1-to-1 ratio, there are a few acid-base reactions that are 2-to-1. If that's the case, then we just have to show this step. 1 mole of HNO3 is 1 mole lithium hydroxide used. There are some cases where you have a strong base where you end up with a 2 here, where this is, if it was calcium hydroxide, then we get a 1-to-2 ratio. We just have to show this step, right? The quick stoichiometry step. So 0.0125 moles of lithium hydroxide used. And we had 0.0136 moles initial. Zero point zero one one 0011 moles excess. So that's how many moles of excess we have. What's the concentration of the excess reactant? That was the one of the trickier problems on the midterm, right? Concentration of the excess reactant. This is what it was setting you up for, was acid-base problems. Because the concentration of the excess reactant is going to determine the pH. So we've got moles of lithium hydroxide. What's our final volume? Yeah, we started with 125 milliliters of the solution, and then we added a solid to it. So our final volume is still 125 mils, right? So at 0.0011 moles. Lithium hydroxide excess. Divided by 0.125 liters. What do we get?
0.008.
Give me one more sig fig.
8.
8.
Yep.
So that's the first 3 steps here, right? This is where we add something new. Because now how do we get to pH? We have a concentration, right? But this is concentration of hydroxide, not acid. If the acid was left over, if the acid was our excess reactant, we would just take the negative log of this number and that's our pH. Just like we did with it initially, right? Once you get the concentration, but if the hydroxide is what's left over, when we take the negative log of it, we don't actually get pH. We get that last weird term that I threw out as everybody was packing up and leaving on Monday. Anybody remember what that was?
No.
I appreciate your candor. POH. POH. P just means negative log of something. So if you can have, if negative log of hydronium is pH, POH is negative log of hydroxide concentration. How does that help us? Well, remember that we also talked about that expression 10 to the minus 14 equals concentration of hydronium times concentration of hydroxide. You remember that? That means if we know the concentration of hydroxide, we also know this concentration if we do a little bit of algebra, right? It means that knowing your hydroxide concentration is just as good as knowing your hydronium concentration. So we could take this 0.0088 and plug it in here. 10 to the minus 14 equals concentration of hydronium times 0.0088. That's this concentration we just found, right? Our concentration of hydroxide is 0.0088. If we know that this relationship is true, if we know this number and we know that that constant is a constant, we can find hydronium concentration that way, right?
Yeah.
Lisa, are you raising your hands? Or just perplexed? Okay, that's reasonable. I'm gonna bring it back a little bit because there's an easier way of doing this. If we do a little bit of algebra with logs here, we can actually take the negative log of both sides of this equation. And then do a little bit of rearranging. We get another form of the same equation that looks a lot easier to deal with. That's 14 equals pH plus POH. Which means, again, as long as you can get either of these concentrations, you can get the other one. So given what's on the board right now, how do we get, what is POH going to be? How do we calculate POH? What's that? We're going to take the negative log of it. Just because we could just take 0.0088 and plug it in here and solve for hydronium concentration like I started with. The more common way to do it is you take the negative log of the hydroxide concentration and you plug it in here, because then you just have to do some quick subtraction. So negative log of 0.0088 2.05. So 2.06 then. Right, so just like with pH, POH is always gonna go to the hundredths place. Regardless of our sig figs, just always take it to the hundredths place. All right, and so this is a good time to practice with your calculator, whatever calculator you're gonna use on the test, practice entering in these logs, make sure you know how to plug the button, push the buttons in the right order. However your calculator works, figure out how to plug in your logs so that you get the right answer. So when you just do log base 10 of 0.0088, you should get negative 2.06. And then just flip the sign because of this negative here. Everybody's calculator's working? Yeah. So what's the pH? So 14 is a constant in water. Technically at room temperature. Temperature changes this number a little bit. We're gonna ignore that. Exactly. So to get pH, if your excess is the hydroxide, we find POH and then just do 14 equals pH plus 2.06. So 14 minus 2.06 is pH.
Oh.
And again, if your acid was what was left over, you find your concentration of the acid and take negative log, and you've already got the pH. pH is sort of arbitrary. Why do we care more about hydronium than hydroxide? We never hear about anybody talking about POH. Because, and we don't even think of that as the alkalinity level. We think of it as how acidic a solution is, right? Basically, because acidic solutions are more common than basic solutions in nature, especially in living organisms in the biosphere. Which I don't use that term very much. Maybe flashback. Anybody remember that movie from the 90s? Biosphere? Oh, it was awful. Is that Pauly Shore? Anyway, because acidic solutions are more common than basic solutions, we rank solutions in their acidity based on pH rather than POH, but they're just as easy to measure.
I was gonna ask if pH.
No, so pH is never a percentage. It doesn't even technically have units. We just say pH units. So we always just write it as pH equals 11.96 or 94, sorry. No, always the hundredths place. All right, so pH problems are really, this is what's called a neutralization reaction. When you add an acid to a base, you get something that's less nasty than either of them individually. So they call that a neutralization because the acid's not as strong and the base isn't as strong as what you started with. So these neutralization reactions, finding the pH after the fact is always just an excess reactant problem. Figure out what runs out first. Figure out the concentration of the excess reactant. And for these problems, especially at this point, it's always going to be a hydroxide and a strong acid. Right? So it's always going to be either your hydroxide is left over and you find POH the way we just did. And if your acid is left over, you find your concentration of excess acid and take the negative log, and that gives you pH. How do we feel about that? Iffy. The only thing we haven't really seen before is this, right? This will take a little getting used to. This is on your equation sheet. So you don't even have to memorize this. Not like it's a particularly complicated equation, and the definition of pH is on there as well.
No, I still have to on this.
Although I think it's written as P of X is negative log of concentration of X. Because anytime you see a lowercase p, it means negative log of something. Okay, the two most common forms are pH and POH. But there'll be some other ones that you run into, especially if you go into biochemistry. We wind up ranking how strong acids are by pKa is a measure of acidity that we'll get into when we talk about equilibrium. All that's to say is this shouldn't scare you. It just means negative log. So px could be anything. So I'm just saying, so pH is negative log of hydronium concentration. POH is negative log of hydroxide concentration. If you see P, a lowercase p, it always just means negative log of something. P nitrate if you wanted to, if you had some reason to do that. Oh, that's why it's not working. Let's do one that's not 1-to-1. Landon? That was moles here minus the moles that got used up. All right. Should we do one where it's not 1-to-1?
Yes, run it us. You're ready.
Literally, the only thing that's different if it's not 1-to-1 is that step where we said 1 mole of nitrate means 1 mole of lithium hydroxide. It's going to be 2-to-1 instead of 1-to-1. The rest of the steps are the same. All right, and so let's work through this. I'm going to give everybody, I'm going to walk around. We're going to do this in small groups. Let's solve this problem. It's going to be very similar to what we already did. Literally, the stoichiometry step is the only thing that's different.
Oh, yeah.
It's really easy when I give you 1 liter of a solution with the molarity, huh? What's that? I already wrote it on the board. What's the molecular weight of the calcium hydroxide? 74?
I thought we 9, yeah. 0.092. Really struggling.
1, 0, 1, 0. Yeah.
009.
Yeah.
Give me 2 more sig figs.
Oh, me too.
For this one, because we started with 3 sig figs on the mass.
Oh, okay.
Only 2 sig figs on the HI because they're
I
concentrated.
keep thinking the 0, so.
Ah, that happens. So what's gonna run out first? We have less than half. It's being used up slower at a 2-to-1 ratio, but we have more than double. Right? So if this is gonna run out first, we can say 0.00983 moles of the hydroxide. For every 1 mole of calcium hydroxide, 1 mole HI used. Or sorry, it's 2 moles. That's literally the only step that's any different than the first problem we did, right? Is that we had this 1 to 2 instead of 1 to 1. So we get one 8166. No, 176.
1, 9, yeah.
There we go. Carrying ones is fine.
Can you round it up?
7.
Yeah, 37 instead of 6.
This one. We need to add another sig fig.
What?
Otherwise, when we do the subtraction and round, it's gonna look like we have nothing left of anything. So just throw another sig fig on here. Pretend like I gave you 0.0200 molar. Otherwise, when we do the subtraction, we're gonna wind up with something that's gonna round. When we round it to the, we rounded it to the thousands place, it's gonna come out to 0. We don't want that. Because taking negative log of 0 doesn't give you an answer that makes sense. So if we have 0.0200 moles of HI and we're using up 0.0197. We get 0.0003 moles HI left. Say that again?
We had to add 2 more zeros on that to make it 366.
No, that's what caused the problem here is because we did subtraction.
Okay.
Subtraction means we keep the uncertainty in the least certain decimal place. So so we only wind up with one sig fig at the end here. All right, final steps. We want the pH. How do we get there? We need concentration. So concentration of HI is going to be how many moles of HI are left. Moles over 1 liter. I just put it in scientific notation so I don't have to write all those zeros. Landon? Divide by the volume, sorry, did I misspeak? Yes, concentration is moles divided by volume, not, otherwise it wouldn't work out, right? We're almost there. If we want the pH, what do we do? This is the concentration of the acid, so we don't have to deal with POH. We do have to do what though? Take the negative log of it. So that should give us something between 3 and 4.
3.5.
On the nose. So always take it to the hundredths place. So there are a number of reasons why the concentration of the excess reactant could wind up being important, especially when you start talking about things like water quality. We can have reactions that cause almost all of the lead in drinking water to be used up and to fall out of solution as a solid that we can filter out. But if there's still some small amount of excess lead dissolved in our water, that's probably not a good thing, right? So finding concentration of excess reactant, it's most obviously useful when we're talking about pH with strong acids and strong bases. But concentrations of excess reactants are always going to wind up being something that's somewhat important. If we wanted to fill out the rest of this box at the bottom here, we did the first 2 boxes here of this table. pH is 3.52. Our concentration of hydronium is 3 times 10 to the minus 4, right?
Yeah.
How do we fill out the other 2 pieces here? Go back to this equation to get POH. 14 equals 3.52 plus POH. So 10.48. Last new thing here. How do we get to hydroxide concentration? We can undo pH or POH. If let's rewrite this here. We can either take that 10 to the minus 14 equals 3 times 10 to the minus 4 times concentration of hydroxide. So divide both sides by 3 times 10 to the minus 4.
Yeah.
What does that give you for hydroxide concentration? There are 2 ways to get there. They will give us slightly different numbers because logs make all these tiny rounding errors bigger. get 3 times 10 to the minus 9. I think.
Yeah. Well, yeah.
Once you round to 1 sig fig.
Yeah.
All right, the other way to do it, if you already have pH and POH, you can also take the POH, because we have this definition. We could plug POH in here and solve for hydroxide concentration that way, but you have to be able to undo logs, which people might not be as comfortable with. We plug in 10.48 here equals negative log of hydroxide concentration. How do we solve for hydroxide? We start by moving that over, right? How do you undo a log? If it's ln, you raise up e to the power of both sides. But this is log base 10, so Gabriella, you use 10 to the power of both sides.
Yeah.
10 to the power of the right-hand side, the log cancels out the 10, you just get hydroxide concentration. So your hydroxide concentration, when we do it this way, we'll get 10 to the negative 10.48. Which if you plug that in, should give you something close to this. It won't be exactly this, though. Because of the rounding issues, plug it in and see how close it is. Is it still 3? Oh, okay. So you do get the same number actually, after you round. A lot of times with logs, when you're dealing with only 1 sig fig, especially, you can wind up with really big rounding errors. And so you might wind up, it should still be times 10 to the minus 9, but you might get 5 times 10 to the minus 9 instead of 3 times 10 to the minus 9 if you go one way versus the other. But as long as they're to the right power and you did your steps properly, either one of those ways should work to find the hydroxide concentration. Is there a limit on how big pH or POH can be? Sorry, hold that thought, Connor.
Read the negative of that.
Good question.
Yeah.
You got negative 11, then that probably means I did the math in my head wrong when we did this. Let's see. 10 to the minus 14 over 3 minus. Yeah, I think I did the math wrong in my head. All right, so logs are pain, but hopefully they're not scary at this point, right? Because at this point, this is the only thing we're using logs for in this class. So as long as you can get to pH from a concentration and then undo it if you need to, that's about all we're using logs for right now. I'm not going to get creative with the word problems for logs. Right? If you see pH, think logs. Beyond that, don't stress out too much about it. All right. So do you have your sheet from yesterday? Did you finish it? So there's your practice. It's more neutralization problems. But I will be happy to work through those with you on Friday. For now, the last thing I want to talk about is what's called a titration, because that's your lab for tomorrow. You did titrations before, huh? Some of you? Wrong keyboard.
Bless you.
All right. So basically a titration is just a neutralization reaction where we're going to add just enough hydroxide. And you can switch the acid and the hydroxide in these. It doesn't really matter. But what we usually do is you're going to start with a hydroxide solution in what's called the burette. The burettes are those big, long, they look like it's one of those. This is a burette, although usually we'll have them vertically for titration. Right, it's just a really long graduated cylinder with a valve at the bottom that may or may not leak. Be careful. And what we're gonna do, the whole purpose for that, the reason why we put the valve on the bottom is so we can add a variable amount of that hydroxide to a solution that has an acid in it. Your acid, we're basically going to add enough of the hydroxide so that they totally cancel each other out. The whole point of the titration is that we're going to stop when we get to what's called the equivalence point. At the equivalence point, you've added just enough hydroxide so that all of your acid is used up. And if you knew your starting concentration of the hydroxide and you know how many milliliters you used, we can use that to figure out how many moles of the acid had to be in there. Right? So if we had say hydrochloric acid and we have an unknown concentration of hydrochloric acid and we're adding sodium hydroxide to it. What are the products going to be for this? H2O and
NaCl.
NaCl. If we don't know how many moles per liter we have over here, a lot of times with these titrations, what we're trying to find is how many moles of one of our reactants we have. And we do that by adding a certain amount of the other reactant. So let's say we did this experiment and we found out that we saw a color change, which is usually our equivalence point. The way we know we reached the equivalence point is we'll put a chemical called an indicator in there, just a couple of drops of an indicator that changes color based on pH. And so as soon as you see a color change and that color change stays, it's going to go from colorless to pink in this case. The most common indicator that we use is called phenolphthalein. And phenolphthalein is colorless in an acidic solution and it's pink in a basic solution. So we're going to add a couple of drops to the acid and it's going to stay colorless. And then it's going to, as we add the hydroxide, as soon as it turns pink and stays pink, we know we added just the right amount of hydroxide. So we know that we have the same number of moles of hydroxide as the moles of the acid. So let's say we had a known concentration of 0.100 moles per liter, and it took I don't know, 23.45 milliliters. How many moles of hydrochloric acid had to get used up? How can we work backwards to figure that out? This is basically the opposite of what we just did, right? Instead of knowing some moles before and seeing what was left over, we're going to say, let's assume there's nothing left over. And if nothing's left over, we know that the moles of hydroxide is equal to the moles of HCl. So all we have to do is use our known concentration in our measured volume that we added to get to moles here. Right, so 23.45 milliliters every 1,000 milliliters is 1 liter, and 1 liter is 0.100 moles. So we wind up with something like 0.002345. 235. Did I slip a decimal or is that right? That looks right. What? We just got moles. It's moles of what? That's our moles of hydroxide. At the equivalence point, if we were careful to only add just enough hydroxide to get it to turn pink and stay pink, then we can say that the moles of hydroxide is equal to the moles of HCl. We added just the right amount. In other words, titrations are a way to figure out how many moles of something you have in an unknown solution. Landon? Say it again. You get that color change. Yeah, basically, so what'll happen is when you're doing this, at first when you're adding it, you'll see a little bit of pink show up right in the middle, right where the drops are hitting, but then it'll disappear again. Because you started seeing a little bit of excess hydroxide in that one little area, but as soon as you swirl it around and mix it, you still have enough acid floating around in there to finish turning it back to being colorless. So as soon as it turns pink and stays pink, we're gonna make the assumption that as long as you didn't overshoot it, as long as you didn't go way past it, then we can make the assumption that those two moles are the same. If you weren't very careful, if it turned pink and stayed pink and then you added another 5 milliliters, we're not at the equivalence point anymore.
One thing, during this lab, sometimes just a few drops will make it very pink versus light pink. Going for. How important is it, you know, if you're just adding a few drops, is that gonna throw your calculations off?
Not that much. When you think about those burettes, a couple of drops out of those burettes, those burettes are usually between 10 and 20 drops as 1 milliliter. So if you have 2 extra drops, you might throw off your hundredths place. You might be off by as much as 1/10 of a milliliter, but your overall numbers are still going to be pretty accurate as long as you're not going way past. So a couple of drops extra is okay. And that's why we do multiple tests and then average them. Right, so what's your actual assignment for tomorrow is you're going to get some white vinegar. And your job is to figure out the molarity of the white vinegar, of the acid in the white vinegar. So, and you can look up on the side of the vinegar bottle, and it usually white vinegar is about 5% by mass. Acetic acid. That's not very many sig figs, and that's also not molarity, right? And so we're going to do a titration to figure that out, where you're going to have a known concentration on your hydroxide, and you're going to do 2 or 3 tests. You're going to do this 2 or 3 times, where you add just enough hydroxide to get your vinegar sample to turn pink and stay pink. And then work backwards to figure out what your concentration must be. Does everybody think they can? It is kind of a fun lab because it has a lot of the classic chemistry things. You get to be dealing with acids, and you get to have color changes, and you get to play with the fun glassware. Glassware is a lot of, especially if you take OChem. OChem is when we get all the fun glassware. You get distillation heads and SOx extractors and.
You have to pay at the college if you break stuff.
Depends on what you break. No, not usually. Usually glassware is factored into our yearly budget. We just have to replace things. It is very kind. When I was in college, we definitely were charged if we broke things.
Say here, bring me Starbucks.
We'll give you the employee rate.
No,
But-
I went to college, my college lab, they gave us a list of all the prices, so it's still got your using, we broke it.
Beakers aren't that bad. Graduated cylinders aren't that bad. Chronicle flasks aren't that bad. Burettes. Burettes are what, $100?
I don't think so.
Not that bad?
20 bucks.
Okay, so. I like to overestimate the cost of the glassware, so you're more careful with it.
Yeah, they're $1,000.
All right. We have 10 minutes, right? So what we'll do